Just a potentially interesting question off of Twitter. Should we be concerned about the flash wearing out, being used so intensively?
Part of Maher's presentation. So one of the things that we have is advanced media management. Actually, is it before this or after this? It's right here.
Is it one of those slides we didn't let you get to?
Yes. So you want to go ahead?
One thing that Rick mentioned here is it's not swap. Why it's not swap? Because if you just simply, for every page that the application requests, if it's not in memory, you have to go just fetch it and come back. There's no way you can achieve the performance level that can get any close to the DRAM on be practical for applications to use, let alone endurance and issues with flash. All right, so if you actually do, for every write you do into memory, you have to write it to flash, yes, you will wear out your flash completely within the first few days. Well, maybe months. But so that's why it's not swap. It is actually the way we think about it is an extension of Virtual Memory Manager. It's a piece of software that works in conjunction with the built-in VMM in the OS to manage pages intelligently, so that application data is available at the right time, in the right location, NUMA-wise, when the application needs it. All right, and it's actually split into two pieces. This virtual manager, the data management piece, which is completely abstracted from the media. It doesn't care about what's the media being we're using to expand memory with its flash, PCM, something else. All what's trying to do is to be one step ahead always from the application and understand what the application is trying to do, its traffic, its profile, its hot data, its cold data, and so on, and do the right thing so that data is as much as possible available for the application in memory when it actually tries to access it. All right, so that piece is, as I said, is completely oblivious, has no idea what's the underlying media is. The second piece, and that's kind of to answer your question, is...
Which, before he goes, is important, I'll tell you why. Because what we've designed will also support emerging memory technologies. Right, so if you remove flash as an underlying media and replace it with RAM or whatever it is that comes out, or 3D XPoint if we had access to it, right, then I guess we would bring out an HPC SKU, right? And now the HPC guys would be potentially interested in that. More expensive, but it'll be faster, and some people will value that, right? So Maher's point here is pretty important. Our architecture, from a software perspective, is completely abstracted. There are two layers. If you took out the flash and replace it with something else, it'll work exactly the same.
The top half will be identical.
The only piece that will be affected is the media management piece.
I don't even know if this is valid. I'm just going to throw it out again. Are you moving memory back and forth between DRAM and your...
Yes.
That's how you're doing it so quick.
Yes, but...
It's just an extension, but you're able to identify that that's DRAM, so I'm going to move it there before it goes.
Exactly. We're using characteristic in the application itself. Oh. So all applications, putting aside synthetic benchmarks that are actually created to be completely random and test corner cases, all applications they have very, very specific criteria. They have clustered data. When they touch a certain piece of data, they actually touch a whole bunch of data together most of the time. So learning that cluster, right away you can see, okay, once I see the application is moving in that region, I'm going to bring that whole piece, because I know with a 95% or 90% certainty he will be touching all these pages again. So clustering learning is one aspect. The other thing is prefetching and trying to predict, okay, he's in this cluster, where's he going next? Okay, and some applications are highly predictable, others are not. And it's equally important to know that this application is not predictable as actually learning a predictable application, because if you start prefetching things that the application doesn't even need, that's even worse. All right. So there's a trick here. You should not. It's very important to not predict sometimes. once you know the application is random.
You're going to inject
right?
latency,
Because you're going to
all
inject
that.
a whole bunch of flash bandwidth that you can get rid of. The other thing is locality of data. We talked about this a lot. By allowing hot data to stay within the same NUMA node where the application is running, that's a huge gain. Because imagine if that piece of data happened to be in the remote node, every transaction to that data now is being taxed by the QPI latency and bandwidth limitation. Whereas if that data happened to make it on the right NUMA node, well, guess what? The first access is 100 microsecond, but then the next 100 other accesses, as long as you can predict that this data is hot and needs to stay in that NUMA node, the next 100 or 200 or thousands of accesses will all be at maximum frequency, at maximum bandwidth and low latency. So you can actually net to be even more advantageous than running in memory directly.
By the way, we call that amortizing a page fault. So the first time you're missing the data could be expensive. And so the CPU will do is it'll park it and say, I don't have it, I gotta go get it. But then subsequent times or subsequent pages, if you're good, it doesn't wait around. So if it's got to do a millisecond of work, it might wait 100 microseconds and then do that millisecond. It might take 1.1 milliseconds instead of a millisecond. That's not so bad. So back to the example that I gave the gentleman about in-memory databases, the first time you move to try to sort a column might take a while to figure out, hey, I don't have the page, I gotta go get it. But then if you know it's gonna use that column, all the rest of the so-called faults will either be minor or there won't be faults at all. They'll basically be minor faults, which means it's in memory, it just has to be mapped, which is done almost instantly. So we call that amortized page faults, which means you pay the penalty once. It doesn't mean you pay it every single time. Something like swap, you pay it every single time, right? So it's completely different, and the reality is in things that take milliseconds or tens of milliseconds because you're analyzing a certain amount of data, we can actually make it run pretty fast because we can amortize the page faults. There's one major, and then they're all minor page faults after that, which go fast.
Yeah, the media management is great for this sort of thing. I guess my concern is that memory can be write intensive. Your device is not going to necessarily be very write intensive. You're not going to be able to sustain that sort of activity.
So that's the second piece here, which is the first piece was just understanding the traffic and making sure that right data is in the right place at the right time for the application. Now the second piece is actually making sure that we do not overload the flash, making sure that we write the flash in a very intelligent way that makes sure that we do not burn it within the next few months. So what do we do to address that? Well, there are two layers. There's a low-level firmware level that runs on the module itself that manages just flash writes and reads and ECC corrections and so on. That's a low-level thing. It has no concept of management of traffic. All right. The really big thing is the other piece, which is the high-level traffic management. We are unlike storage. It's not any type of traffic. We control the traffic that's going to the flash. We take the third traffic, we shape it. I'm sure you guys are aware that sequential traffic is much better than random. I mean, sequential is, if you guarantee sequential traffic going to flash, you're guaranteeing a write amplification of 1, meaning you right away have increased the life of flash by 4, 5, 6, 7 times even, depending on the OP you're doing. So by us sitting in the middle between the application and implementing a remapping layer, we can actually fully sequentialize the traffic that's going to the flash. So no matter how random, no matter how much traffic the application is throwing at us, that random traffic will always be sequential going to flash. So that's.
I understand the sequential writes are going to happen. I understand you're going to get the whole.
It's coming.
The other thing is making sure
It's coming, Ray. Come on.
dirty page write management. That is the piece that I think will address your question. Is today the way what we do is we make sure that any hot pages, any pages that are frequently accessed by the application remain in memory. Well, what we add on top of that is dirty page preference. What that means is if we have pages that are high frequency accessed and dirty, we make sure that they stay in memory as long as we can. They will be the last pages ever evicted. So if the application is writing a page,
or never evicted,
or even never evicted if we can't afford to do that. All right. So if a page is being written millions of times every second, guess what? That page will never make it out of memory because we have detected that it's a high frequency page and it's a dirty page. And guess what? That page will always remain.
This is all within your.
It'll remain where?
Your card,
In memory.
right? This
It will never be evicted to flash.
This is the software
It will never write it to flash.
around your card.
Move it to DRAM
This
so it'll
is
keep the wear
this
off
is
of
between the
That's
operating system and our hardware. So I want to explain this. This is really important. I want to make sure you understand. We wanted to show you a graph. Okay? The gray is writes. The red is reads. Okay? This is to our flash that we're measuring to the flash. We disabled the feature, and then we turned it on right here. You see there's a pretty major inflection point, right? So we turned it on right there, okay? Now, the reason that this is 50-50 traffic is because a write to a random page means that you have to read it in from flash, dirty it, and then evict it back to the flash. Okay? So just to be clear, we kind of skipped over a little bit of this. Actually, the thing I hate the most, which is going to be our next science project, okay, is if I had one thing that I wish we didn't have to do, is when we write data randomly, we have to freaking read it, modify, and write it back. By the way, Intel, we know, by trial and error, mistakes, scars, God knows what, the things that Intel does. Well, it turns out that Intel does read, modify, writes on RAM constantly. When they cache stuff, they read in all kinds of stuff, they modify it, write it back. You rarely actually just write to the RAM. It's a read, modify, write, okay? It's okay because reading from RAM's fast. Reading from flash is 100 microseconds. It's a pain in the butt. So it's 50-50 traffic. If you're doing writes, it's 50-50 traffic. Now, what we did was we set up some threads that are writing. All they're doing is like read, write, writes, 50-50, just read, write, writes. And then we turned on the feature. Well, look at the writes basically start to collapse to 0. Now, you are writing all day, all night to this so-called flash, but you're not writing to the flash.
Random
Yes.
addresses.
Okay? If your application is writing, we will map those into RAM. Okay, and we will reduce the writes to the flash. Now, if you have an application that all it does is writes all day, completely random, you shouldn't buy Memory1. If you have an application that does 90% reads, 10% writes, 80% reads, 20% writes, something like that, then I got a solution for you. Now, this means that because, again, it's not flash. It's flash working in tandem with DRAM in the system to give you expanded memory. That means that we can, under specific circumstances, have infinite endurance. Okay? So the important thing is if you have a little database thing and it's constantly updating a tree structure, well, the tree structure will never be evicted from the flash, from the RAM, and you can write it all day and all night. You can update it all day and all night. We won't care.
We detect highly frequently written pages and keep them to RAM so that they never get evicted to flash and therefore
Exactly.
That makes
you can
sense.
write.
So again, if you're writing totally random, all day, all night, 24/7, don't buy Memory1. I'm okay with that because I don't know a customer that does that. Or if they do, it's called a log, and they got to put that on some NVDIM, and they're not buying a lot of them anyway, right? There are reasons that people, if they're writing metadata constantly all day and all night, they got to use something else. But that's not a tool for memory expansion. It's not an application, right? So what is important about this is if you do have like an in-memory database, there will be updates, there will be writes, they're going to come in. There's a good chance that they're going to be hot, and they will not make it to the flash. And that's how we have it. Now to do this, we actually use hardware in the CPU that tells you, hey, this page is dirty, it's different from what's in the flash, and we can detect it and we can do something special with it. It's not something you would do in the storage world, but in the memory world, we can do this. So hopefully this addresses the concern. You can write all day and all night. Again, if you did it to every address in the space, it wouldn't work. But that's not an application that you would support with our product anyway, right? So this is, I knew the question would come up, and that's why we did it. And again, this is measured data, you know, and I just want you guys to understand, this is a pretty sophisticated product. It's designed to withstand usage over years, you know, and of course you're reading and you're writing constantly, right? So hopefully that answers your question, right?